Welcome to Fundamentals of Convection. Build your foundation in convection. Let's begin by understanding why convection is so important in heat transfer. Convection governs how heat moves between surfaces and fluids, making it critical in real-world systems, whether it's cooling electronics, heating fluids, or designing energy-efficient buildings. In this session, we'll focus on the fundamental concepts, keeping things simple yet powerful. You'll learn the key principles, explore essential equations, and understand how convection interacts with conduction and radiation. Mastering convection means mastering practical heat transfer. Let's make sure every concept is clear and applicable from the start. Let's clarify exactly what you'll gain from this session. First, you'll understand the mechanism of convection and how to classify it. You'll see the importance of velocity and thermal boundary layers and master critical dimensionless numbers like Reynolds, Prandtl, and Nusselt. You'll be able to differentiate laminar from turbulent flow, derive equations from the basic principles of mass, momentum, and energy, and solve simple practical problems like flat plate convection. Finally, you'll connect fluid flow and heat transfer using analogies, a key engineering shortcut for estimating heat transfer coefficients quickly and effectively. Focus on these targets and you'll master convection with confidence. 2. Build a strong foundation with convection basics. Let's begin with the fundamentals. Convection is more than just heat transfer. It's a combination of conduction through fluid layers and advection due to fluid motion. A key principle is Newton's law of cooling, which shows how heat transfer rate is proportional to temperature difference, governed by the heat transfer coefficient H. What affects this? 3 key things: fluid properties like viscosity and thermal conductivity, flow velocity. Faster flow usually means more heat transfer. Surface effects. Roughness and geometry can enhance or hinder the process. Master these basics and you'll have a solid grip on real-world convection problems. 3. Classify convection like a pro. Let's simplify convection by classifying it smartly. First, based on fluid motion. Forced convection happens when pumps or fans push the fluid. Natural convection occurs naturally, driven by buoyancy effects, like hot air rising. Second, based on flow type. External flow is when fluid moves over a surface, like wind across a wing. Internal flow is when fluid moves inside pipes or ducts. By organizing convection this way, you'll quickly know which equations and assumptions to use for any engineering problem. 4. Master boundary layers to understand convection. Let's break down boundary layers, a core concept in convection. No slip condition means fluid at a solid surface has zero velocity. It sticks to the surface. Velocity boundary layer is where velocity shifts from 0 to the free stream value. As you move downstream, this layer gets thicker. Thermal boundary layer forms where temperature changes happen. Its thickness depends on the Prandtl number. Formula: delta over delta T, approximately PR to the 1/3 power. Thin for fluids with high thermal conductivity, PR less than 1, but thick for fluids with high viscosity, PR greater than 1. Remember, knowing these layers helps predict how fast heat and momentum travel through a fluid. 5. Master the key dimensionless numbers. Let's simplify 3 essential dimensionless numbers you'll see in convection. Reynolds number, Re, tells us if the flow is laminar or turbulent. Formula: Re equals VL divided by nu. Laminar flow is Re less than 5 times 10 to the 5th, and turbulent flow is Re greater than 5 times 10 to the 5th. Prandtl number, PR, compares momentum diffusion to thermal diffusion. Formula: PR equals Cp mu divided by K. PR less than 1 is when heat diffuses faster, for example, liquid metals, and PR greater than 1 is when momentum diffuses faster, for example, oils. Nusselt number, Nu, shows how much convection boosts heat transfer. Formula, Nu equals HL divided by K. Nu equals 1 is pure conduction, but Nu greater than 1 is convection enhances heat transfer. Remember, these numbers quickly describe flow behavior and heat transfer efficiency. 6. Clarify laminar versus turbulent flow. Let's break down the two types of fluid flow so you can instantly tell the difference. Laminar flow, smooth and orderly flow with parallel streamlines, results in lower heat transfer since there's less mixing of fluid layers. Turbulent flow, chaotic and energetic with swirling eddies and high fluid mixing, delivers much higher heat and momentum transfer due to stronger mixing. Reynolds number transition points. Flat plate. Flow becomes turbulent when RE exceeds 5 times 10 to the 5th. Pipe. Flow transitions to turbulent above RE equals 4,000. Recognize the type of flow quickly. This will guide your heat transfer predictions. 7. Simplify the governing equations. Understanding convection starts with 3 fundamental equations. Continuity equation governs mass conservation, ensuring fluid in equals fluid out. Momentum equation, Navier-Stokes, governs how velocity changes due to forces like pressure and viscosity. Energy equation governs temperature distribution within the flowing fluid. In boundary layer flows, we simplify these equations because temperature change along the surface, dt over dx, is much smaller than temperature change perpendicular to the surface, dt over dy. Focus on these simplifications. They help you solve real-world convection problems efficiently. 8. Make heat transfer more practical. Let's simplify laminar boundary layer theory using the Blasius solution. This approach gives practical formulas for flow over a flat plate. Velocity boundary layer thickness, delta, scales with distance, x, and local Reynolds number, Rex. Expect delta to grow downstream. Local friction coefficient, CF, predicts surface shear stress, inversely proportional to square root Rex. Local Nusselt number, NUX, quantifies local heat transfer rate, depends on both Rex and Prandtl number, PR. For thermal boundary layer thickness, delta T, it's thinner than delta for high thermal diffusivity, low PRAR, highlighting the role of fluid properties. Focus on these key equations. They connect theory directly to practical heat transfer analysis.
7.1. Understand dimensions and units clearly. Before we get into formulas, it's crucial to understand what we're actually measuring. Dimensions describe what you're measuring without numbers, like length, mass, or time. Units, on the other hand, give dimensions a number, like meters or seconds. Focus on the 7 primary dimensions: mass, length, time, temperature, electric current, light, and amount of matter, or N. Everything else, like force or energy, is built from these. Why is this important? Because dimensional consistency keeps your equations valid. You'll also learn how derived dimensions simplify your work and prevent calculation mistakes.
10. Link theory to real engineering impact. Let's see how convection plays out in the real world. Electronics cooling. Fans and heat sinks keep devices from overheating by boosting convection efficiency. Airfoil and wing heating. Essential in aerospace to prevent ice formation, ensuring safe and efficient flight. Food cooling and heating. Industrial ovens and chillers rely on precise control of convection for uniform cooking. Heat exchangers. Maximizing the Nusselt number, And U leads to superior performance, making systems more energy efficient. By mastering these applications, you'll bridge the gap between classroom theory and engineering practice. 11. Clarify microscale heat transfer concepts. Let's wrap up by zooming in on the microscale. The Knudsen number, Kn, helps us decide if continuum mechanics applies. Kn less than 0.001, classical fluid mechanics is valid. Continuum assumptions hold. Kn greater than 0.1, we enter the realm of rarefied gas flow, where non-continuum effects dominate. Phonon transport takes over at nanoscale, making conduction mechanisms quite different from bulk materials. Microchannels in advanced devices require specialized convection models. Standard formulas simply don't apply. Understanding these nuances equips you to handle modern engineering challenges in microelectronics and nanotechnology. 12. Summarize the key takeaways. Let's conclude with a quick recap of the essentials. Convection requires fluid motion divided into natural and force types. Boundary layers form, shaping both velocity and temperature profiles. Dimensionless numbers, Reynolds, Prandtl, and Nusselt, make it easier to analyze different flow situations. Turbulent flow boosts heat transfer, though it comes at a higher energy cost. Momentum and heat transfer are linked, giving rise to useful analogies like Reynolds and Chilton-Colbin. Microscale convection behaves very differently, requiring models beyond classical theory. Mastering these points equips you for advanced problem-solving in convection heat transfer.